All right, people. Let's go ahead and jump into today's lecture. So, as promised, last lecture, Friday, was all about ionic bonding. We talked about lattice energy, which is the relationship between the attraction of two ions, the positive and the negative attracting each other. More charge, higher lattice energy, smaller radius, more lattice energy. Then we talked about electronegativity, which is the attraction for shared electrons. We said when there's a big difference, that's when you have one atom taking the electron from another one. We form a positive and negative ions. But when the electronegativity difference is smaller, when atoms have similar electronegativities, they share electrons. And when they share electrons, what happens is that we form what we call a covalent bond. Okay. So a covalent bond is the attraction of the nuclei of two atoms for a shared pair of electrons. All right. So you got the electrons in the middle, you got the nuclei, they're positive, the electrons are negative, they attract. Okay. So what happens is that there is a release of energy as these two atoms interact and share electrons. One of the things we want to understand is what's this type of what's known as a potential energy internuclear distance diagram. All right. We imagine we start off far on the right hand side. The atoms are far, far apart. Okay. Infinitely far apart. They have no interaction. This is what we call our 0 point. That's our zero energy. The atoms are far apart, not interacting. As the atoms come closer together, their orbitals begin to overlap, and the electrons begin to be paired and shared between the two nuclei. It's what we would call a bonding orbital. And that pair of electrons between the two atoms pulls the atoms together and they lose energy. They release energy. Okay. So as the atoms get closer together, they release more and more energy as the nuclei are attracted to those pair of electrons between them. Okay. At some point, we hit this minimum energy. This is what we would call the bond energy, the amount of energy released as the covalent bond forms. Okay. This is going to depend on the amount of charge. So you can have two electrons or four electrons or six electrons. There you can have up to what we would call a triple bond in this sharing of electrons scenario. Okay. It's also going to depend on the size of the atoms. The bigger the atom, they can't get as close together, the weaker the bond energy would be. So for this graph, there are two aspects of it. The depth here is controlled primarily by the number of electrons, the amount of charge being shared. And then the horizontal axis is primarily controlled by the atomic radius. There is a little interplay there because, of course, small atoms can get closer together, which ups the attractive force, right? Coulomb's law attractive force. Now, when you look at this, though, so that was describing what happens as the atoms come together and we reach this minimum point. If you start shoving the atoms closer together, we start climbing this end, and you can see the energy goes back up quite steeply. Right? What's happening as these atoms get closer and closer together is now the nuclei of the two atoms are beginning to get close, and the positive charges in the nuclei start to repel each other. Okay. So as you start getting closer and closer together, the repulsive force of the positive charges in the nuclei begin to push the nuclei apart. And so the bottom of this well, the average bond length and strength, is determined by that balance between the attraction of the nuclei for the electrons in the middle and the repulsion of the nuclei for each other. All right. So in this graph, and we will see some examples. We'll do some worksheets where we look at these because we can begin to reference this and talk about how strong the bond is, how much energy is given off, and the bond length as the distance between the two nuclei. Okay, but before we get deeper into these graphs and talking about bond lengths and strengths and stuff like that, we need to understand a little bit about how we are going to model the behavior of covalent bonds. When I give you a chemical formula, you need to be able to write down a sort of diagram that shows how are these atoms covalently bonded together. All right. And there are a couple of different models that we could potentially use. A big distinguisher between them is whether they are localized or delocalized. And what we mean by that, in a localized model, we are pretending we know exactly where the electrons are. Okay. So we say, hey, I know where the electrons are. I can draw them exactly in position. So for instance, the model that we're going to spend most of our time using was developed by a guy named Gilbert Newton Lewis up at UC Berkeley at the turn of the century, in the late 20s, early 30s. And it is focused on dealing with valence electrons. All right. So remember when we look at our periodic tables, the valence electrons are the ones in the highest energy level. I've said a couple of times, those are the ones where they're going to do all the chemistry work. Okay. So we know that the maximum number of valence electrons, if we count across, right? 1, 2, 3, 4, 5, 6, 7, 8, takes 8 valence electrons to fill up that valence shell. Then you have to switch to a new energy level. So the key here is the number 8, all right, what we call octets, all right? So we take our symbol from the periodic table and we imagine 4 pairs of boxes around the top, bottom, left, right of the atom. Each of these boxes, pairs of boxes, can have an electron in it or not. Okay? So, for instance, oxygen. Find oxygen on the periodic table. Count from the left. 1, 2, 3, 4, 5, 6. Oxygen is 6 boxes from the left side. Oxygen has 6 valence electrons. So I imagine the boxes. I put those imaginary boxes. We don't generally draw them. We visualize them in our heads. And I put 1, 2, 3, 4, 5, 6. 6 electrons, 6 dots. We use a dot to represent an electron. Notice how I did that. I put 1 on each side before I paired up. Okay. So the idea here again, each of these pairs of boxes roughly represents an orbital of some kind, and we'll put 1 in each before we pair them up. All right. So oxygen, take away the boxes, and we've got our what we would call a Lewis dot diagram for oxygen. Oxygen has 6 valence electrons. You can see visually that there are 2 spots where oxygen is missing electrons from filling up its valence shell. Those are the 2 spots that need to get essentially filled up by chemical bonding. All right. So, for instance, in a simple case, hydrogen, 1 electron. Okay. First energy level, you can see it's a special energy level because it only has 2 boxes, 2 electrons in the valence shell for 1s. So if these 2 hydrogens come together, they could share those electrons as a pair. And we typically, depends a little bit on the notation style, I like to use a line to represent that chemical bond. So a pair of electrons shared between atoms is what we're going to represent as a chemical bond. All of this is what we would call a localized electron model. It is pretending that we can put electrons in specific places, that we can identify exactly where they are, and we can go ahead and do that. Of course, we know that that is not a great model because electrons, if you want to explain energy levels and orbitals and all the stuff we've talked about last unit around electrons, we need to think about quantum mechanics, and we talk about the probability of finding the electron. And a delocalized model is a better model for understanding how atoms form molecules. And there's a whole branch of chemistry that deals with these types of what we would call molecular orbitals. We'll talk a teensy bit about it later on. But for first year chemistry, we can't do this. We don't have quantum mechanics. You don't have calculus. We focus on the model that we can apply. It works and tells us a lot of useful information. It does have limitations that we'll have to talk about. Okay. So in this kind of thing, we are talking about overlap and changes in orbital structure, and we're not trying to say we know exactly where the electrons are, talk about probabilities and fun stuff like that. So just be aware that the Lewis structures that we're going to spend most of our unit talking about, while fine as an introductory model, leave a lot to be desired in predicting how molecules actually behave, where electrons are actually likely to be found, and the energies that they have. Okay? All right. So, operationally, what do we need to be able to do? You need to be able to draw what we call a Lewis dot diagram or a Lewis structure. This starts off with a chemical formula. This is hydrogen fluoride. Okay? So, hydrogen fluoride is hydrogen bonded to fluorine. They're both nonmetals. Okay, so we can consider these both nonmetals. They have similar electronegativities. Okay, in the gas phase, they are going to be held together by covalent bonds. Okay, now let us think about how we can figure out those covalent bonds. And I'm going to teach you a process to go through. Okay. The process starts by counting up how many valence electrons does each atom have. So I grab my periodic table. I find hydrogen, 1 electron in hydrogen. I find fluorine. I count from the left, 1, 2, 3, 4, 5, 6, 7. Fluorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. Now, you may have done stuff like this in middle school. It's relatively common to treat these kind of like jigsaw puzzles. And you try and fit them together. That's not how we're going to do it because that process doesn't give you the tools you need to deal with more complex scenarios. So we're not going to jigsaw puzzle this. What we're going to do is we're going to count how many total valence electrons do we have. So 1 from hydrogen, 7 from fluorine, count them up, get that number. There are a total of 8 valence electrons. Those are the electrons I can use. Those are the electrons that all have to get distributed into my molecule. In general, the molecules that they are going to ask you to draw are going to have a central atom with other things connected to it. Very occasionally, they will do things where you have a carbon backbone, 2 or 3 carbons connected together, and then things attached to the carbons. That's not as common. Okay. We generally limit ourselves to doing a central atom with stuff connected to it. The first element listed in the chemical formula, that's not hydrogen. Hydrogen can never be your central atom because of hydrogen being in the first energy level. It can only ever form a single bond. It can't be your central atom. So you look at your chemical formula and say, what's the first element listed that's not hydrogen? Fluorine. So I put fluorine down, okay? Right? F. And then I say to myself, okay, I want to take all the other elements in the molecule and I want to surround that central atom with them. So I'm going to put 1 on each side. And then I'm going to draw a line which is a pair of electrons. So I'm going to take two of my electrons from my pile, and I'm going to turn them into a chemical bond. All right. Now I do that for each of the atoms. And now I take the rest of the valence electrons and I'm going to put them into my model as dots, indicating what we call non-bonding electrons. These are electrons that are not forming chemical bonds. We're sometimes referred to as lone pair, sometimes non-bonding, that kind of thing. Okay. So the goal is for every element to have at least 8 electrons around it, indicating that it has a full valence shell. There are some exceptions. The very first and most important exception is hydrogen. Hydrogen, only the 1s needs to be filled up. 1s takes 2 electrons to fill it up. So hydrogen only gets 2 electrons. In this model right now, hydrogen has 2 electrons around it. Remember that the bond always represents a pair of electrons. So this hydrogen has 2 electrons around it. The reason why all of this works is because the bonds get to count for each atom that they're connected to. So right now, this fluorine has 2 electrons around it. To fulfill the octet rule, fluorine needs 6 more electrons. I have 6 more dots. So I'm going to go through here and put these dots in around the fluorine and put 2 on each side. When I run out of dots, I can't add more. I can't change the number of valence electrons. It is what it is. Okay? So now I check. Have I fulfilled the octet rule? Fluorine has 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. That follows the octet rule. Awesome. What about hydrogen? 1, 2 electrons. 2 electrons is all hydrogen needs. Okay? There are some other exceptions that we will talk more about tomorrow. Today, we're going to focus on following the rules, building models that follow the octet rule, except for hydrogen, which follows what's sometimes referred to as the duet rule, not necessarily super relevant. So let's work together and do a couple of examples here. Okay. First of all, let's talk about methane, CH4. All right. So in your example box, write down CH4 or on the back, doesn't matter. We got to practice. Step 1. How many valence electrons do you have to play around with? So look at carbon, find carbon on the periodic table, count up how many valence electrons does carbon have. Write that down. Write it down. Like, don't try and do all this in your head until you've practiced a bunch more. So carbon, colon, check the valence electrons. Carbon's got 4 valence electrons. And this is the key. We're not looking at the atomic number. We only want valence electrons, only the ones in the highest energy level. The easiest way to get them, find the element and count to the left. 1, 2, 3, 4. Okay, just the ones on the highest energy level. Hydrogen is relatively straightforward. It only has 1 electron. But how many hydrogens are there in this chemical formula? So I got to take the 1 electron for each hydrogen and multiply by 4. Altogether, I have 8 valence electrons. Okay, 8 valence electrons altogether. Now, step 2, figure out what the central atom is. The first element listed that's not hydrogen, carbon. Write down carbon in the middle. How many hydrogens do I need to put around that carbon? All 4 of them. So 1, 2, 3, 4. Write that down. Each carbon and hydrogen get a line indicating a pair of electrons holding the carbon and the hydrogen together. So I draw a line. 1, 2, 3, 4. Draw 4 lines. 1, 2, 3, 4. How many electrons have I used up to form those bonds? 8 electrons. That's all the electrons I got. So hopefully this works. Check your octet rule. This carbon has 8 electrons around it. That's good. Each hydrogen has 2. That's good. We followed the octet rule. This is a valid Lewis structure. So this is a Lewis structure for methane, CH4. Now, at the beginning of this lecture, I said, hey, you can share more than 2 electrons. It's possible to share 4 electrons or even 6. Okay. And we do that by using multiple lines between the atoms. Okay. What we call a double or a triple bond. Let's look at an example of how we would get to a double or a triple bond. Nitrogen, N2. Write down N2 on your lecture notes. Find nitrogen on the periodic table. Figure out how many valence electrons it has. Write that down. How many valence electrons does nitrogen have? 5 valence electrons. Again, find it on the periodic table. Count. 1, 2, 3, 4, 5. You count from the left. Okay, it's not the total number. You just count from the left of the row it's on. So here's my nitrogen. I count 1, 2, 3, 4, 5. 5 valence electrons for each nitrogen. Okay, how many nitrogens are there? 2 of them. Altogether, I have 10 valence electrons. Now, in this case, nitrogen and nitrogen, there's only 2 atoms. Neither of them is the central atom. They're just equivalent, right? So I'm going to put a nitrogen down. I'm going to put a second nitrogen next to it. I'm going to put a single bond. All right. So that's the next step. How many electrons did I use to form these bonds? So how many do I have left? 8. So I'm going to put 8 electrons around. Okay. The way to do this, if you have a central atom, put your electrons on the outside atoms first. You'll find out that that will tend to make it easier to figure out multiple bonds if necessary. So I'm going to put them in 1, 2, 3, 4, 5, 6, 7, 8. That's it. I can't put any more dots. I only had 8 electrons left. This nitrogen on the right-hand side, how many electrons does it have around it in this structure? How many total electrons around it? 8. 2, 4, 6, the bond counts. 8. Okay? So this nitrogen has 6 non-bonding electrons, or 3 non-bonding pairs, and 1 bonding pair, total of 8. It's following the octet rule. Awesome. But on the left-hand side, this nitrogen has only 4 electrons around it. It's not following the octet rule. That's not okay. We need to get more electrons over here. The way to do that is getting more electrons to share between the atoms. So what I'm going to do is I'm going to take 2 electrons off of this nitrogen, and I'm going to turn them into a bond. Now notice this nitrogen on the right still has 8 electrons. 2, 4, 6, 8. Each line represents 2 electrons. The nitrogen on the left, 2, 4, 6. It's getting closer. Everybody's got to get to 8. I'm not there yet. So I can take another pair off of this nitrogen and turn it into a third bond. Triple bonds are the max. Why? I will explain later. It has to do with orbitals and how they can overlap. So now this nitrogen has a triple bond Each nitrogen has 2, 4, 6, 8. 2, 4, 6, 8. Yeah, I get to count the bonds twice. When you're sharing, you get to count for each atom. That's kind of how this whole system works. The shared bond electrons count for each atom. This is each nitrogen is following the octet rule, valid Lewis structure. This is the Lewis structure for nitrogen. Quick question. Which of these bonds, a carbon hydrogen bond or a nitrogen nitrogen bond, do you think would be stronger? Don't say anything. Think about it for a sec. Which of these bonds would be stronger and why? Talk to your neighbor. Talk to your neighbor. When we started back at the beginning of the period, what did I say determines how strong the bond is? Charge. Charge and radius. Okay. Charge and radius are the two things we're looking for. Okay. Charge and radius. So, how much charge is between these two nitrogens? One, two, three, four, five, six. 6 electrons, 6 negative charge. So there is 6 charge roughly between these two nitrogens. How much charge between the carbon and the hydrogen? Just two. Just two. One bond, 2 electrons. It's a -2 charge. Coulomb's law, more charge, greater attractive force. This bond is substantially stronger than this bond. Yeah, the hydrogen is small. That's true. And it will affect this, but this has 3 times the charge that this bond has, right? 2 electrons versus 6 electrons. More charge, stronger bond. Okay. All right. That is it in terms of introduction to Lewis structures. Okay. You now have the tools you need. Count those valence electrons, central atom, surround with the others, single bonds, put in the dots. Remember, we think of the 4 sides. Everybody's got to get to 8. It doesn't matter where you start. I suggest you start on the outside. The atom's not the central atom. Hydrogen is our exception, only 2. There are more exceptions, but tomorrow's whole lecture is exceptions to the octet rule. So.